Okay, so topic 12, another pretty simple one once you get the hang of it. This is to calculate the line integral for scalar functions and vector field directly. So there's two parts to this topic and we're gonna do it in order. So scalar functions first. Oh, I'm gonna get my pointer. Scalar functions first, right? What we're gonna be given is z equals f of xy, which is called our density function. And we're also going to be given a c, which is c is really equal to r, and r of t is equal to x of t and y of t. And then we're going to be given a bounds, right? So I noted here that C is a curve to be parameterized because sometimes it's given to us already as a parametric equation, already parameterized, and sometimes it's not. So we have to do a little bit more work. But our formula is right here. And I said just remember that the magnitude of R is just the square root of x squared plus y squared, and then magnitude of r prime is just x prime squared, or square root of x prime squared plus y prime squared, right? And then I rewrote it just so we can substitute easier. We have an example right here. Given f of x, y, z equals x squared plus y squared plus z squared, and r of t equals cosine t, sine t, and t, and these bounds, find the line integral. Okay, so we can notice that this curve has already been parameterized because we can easily tell what our x is and what our y is and what our z is. So let's solve it. So first thing we did was rewrite it. Rewrite the integral from 0 to pi. And then this portion of the problem right here would be this, right? Would be this. But instead of writing x squared plus y squared plus z, we substitute the x's and y's and z's, right? Into here, into there. And then we get this, right? So that's the first portion. That's this first portion. Now we work on the second portion with the square root, okay? This portion right here. And mind that this is the derivatives of x and y. So we take the derivative of this. So that's negative sine. Okay, and this is cosine. And this is just 1. All right, and then we square, dt. Okay, so we notice that this is a cosine, and that's an identity. So that's 1. And this is also going to be 1, right? So we can simplify that into 1 and t squared, 1 plus t squared. And this we can simplify to 1 plus 1 equals 2. So square root of 2. And then we solve it as usual. And we get this answer right here. So pretty quick and easy. Let's go to a bit of a harder example. Not hard at all, but let's do it. So given f of xy, you got a square root right there. That's your f of xy. And then you're given this right here, right? And then you're given bounds. So notice how this is not parameterized because you can't tell what your x, y, z is. You can't substitute anything into anything. Okay. One thing about this scalar functions is like this problem, you want everything to be with respect to t. That's why you substituted in the first place. You want everything to be with respect to t. So that's what we want to do here. That's the purpose of this. Our goal is to convert y of f of x, which is in this particular problem that, right, into two separate functions of t, which is x equals a of t and y equals b of t, so that we can substitute these values into our limit. Okay, so the easiest way to do that is to just let x equal to t. And if you do that, if for example, you want to parameterize this, if you do x equals t, then you substitute t into there, right? You just get y equals that. Very easy. So you got an x with a t and a y with that. And that's parameterized, right? Very easy to see where your x and y is. You can substitute it. So going back to our original problem right there. Okay, I just parameterize this to become this. There are many different ways to parameterize an equation. You could have used like x to the 15th if you wanted to, but why would you do that, right? Just more exponents for you. So okay, we have our curve right here. Yeah, parameterized curve to use, and this is what we're going to substitute into our thing. Okay, I hope we see how exactly I did that. And again, I rewrite my integral. I start writing my integrals from 0 to 1, and then I substitute as usual. And I'm sorry, I should have rewritten this here, but I basically use that, right? I basically use that and just substitute it into there. And again, instead of xy, we want it to be with respect to t, so xy, right? I substituted these values to there. And then the second portion again of our problem is just the derivatives squared, right, under a square root, and then dt. And then we solve as usual, and then we get our answer.